Now the same idea, the time is discretized from 0 to 30 seconds, right? And we have the velocity at every 5 seconds. The velocity is given in mile over hours. And the question is to compute the distance over 30 seconds. Okay? If we want to compute it in terms of feet per second, right? This is mile over hour. And let us compute it in feet over second, okay? It means that we need to change all the velocity in terms of mile over hours to be feet over second. So remember now, 1 hour, 1 mile, over hour. It is equivalent to 5280 over 3600. And here's feet over second. Because 1 mile is equal to 5280 feet, and 1 hour is equal to 3600. Okay? Now, this is 1 mile. It would be equal to this guy. Okay? We have this. The same story. Now, before doing this, if you don't remember, let us play with a small example. 1 pen cost $5. How much do we need to pay to get 2 pens? $10, right? $10. So the rule is this: multiply 2 multiply 5 and divided by 1. So which is $10. This is how to memorize to get a result of these types of problems. Proportional rules. Okay? Or if you want to know how much you need to pay to get 3 pens, what should we do? The same story. We pick this number, 3, right? Multiply 3 and divide it by 1. 3 multiplied 5 divided by 1, which is $15. Okay? Or sometimes we don't need to find the price of 1 pen. We can do faster by doing this. 3 multiplied 10 divided by 2, right? it gives us the same result, 15. Okay? We don't have to memorize it. If you understand this, you can deal with similar problems for any problems. Okay? Now in our problems here, the same logic. Look at this. This is 17 miles, right? We know that 1 mile will be this much. 1 mile over hour will be, so same story. 1 mile over hour is equivalent to 5,200 divided by 5,280 divided by 3,600 feet per second. The question is, how fast is it when we are given that the velocity is 17 miles over hour? What do we have? The same logic. This one multiplied with this number, right? Divided by this number, and this gives us the result. It would be 17 multiplied 5,280, 3,600, and then divided by 1. Okay? Can you do it yourself and tell me what number you have here? If we're given that, perfect, Gary. Or we approximate it and, okay, round it up a little bit. It will be 25 feet per second. Okay? And the same logic. If we are, the velocity is 21, then mile per hour, it will be 31 feet per second. Here's 35, 43, 47, 45, and 41. Okay? We know the tables, right? Then imagine it is similar to a graph of velocity and time, right? Did you got the numbers here? Okay, very good. So imagine that we have the graph of velocity with respect to time here from 0 to 30 seconds, right? Five, 10, 15, 20, 25, 30. Then we know the value of velocity. It is 25, 31, 35. It is increasing, right? It is somehow like this, right? So we want to compute the distance. According to the formulas, it will be, there are two methods, the left approximation and the right approximation, right? And let us call the distance. It will be sum from I is yeah, is equal to 1 to the n of f at the time t I minus 1 multiply delta t. That is the first of the, yeah, the limit. There's a limit here, sorry. Or in our case, let us, is I run from 1, 2, 3, 4, 5, 6, 7, right? If we mark it 0, or T0 here, T1, T2, T3, T5, T6, T7, then it would be T1 to 7 here, right? In our case, that is the first method. Or let us call it D1. It will be f of T0, right? Multiply delta T plus f of T1 delta T plus etc. until f of T6 delta T. Sorry, it runs from I is equal to 1 to 6. Oh, to 7, I'm sorry. Right. And here, the function f is velocity, yeah. Say it again, please.
On the graph, it's T4. You go from T3 to T5.
Oh, my bad. Thank you. That's right. That's why. 4, 5. Yeah, we need to take a counting class. Thank you. So therefore, it will be from 1, 2, 3, 4, 5, 6, right? Yeah, makes sense now. So it will stop at T5. Sorry. Very good, Vikram. So then we know owns the values, right? Just plug in them in and we can compute the value. Is it clear, the idea? Is the idea clear? Then go home and double check if it is equal to, yeah, it's 25, 31 here, right? It will be 25 times 5 plus 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 45 times 5, and it is 1130 feet. Okay. So you can go home and double check this result. But is it clear now? And another approximation is we approximate the distance to be the right value, and it is the sums from I is equal to 1 to 6 of f of ti multiply delta t, right? And it will be f of t1 delta t plus f of t2 delta t, etc. until f of t6 delta t. T1 is 31, delta t is 5, plus 35 multiplied 5, plus 43 times 5, plus 47 times 5, plus 45 times 5, plus 41 times 5, and we got 1210 feet. Okay. These are two approximations. Or you can do it yourself if we do an average. Look at this. Do you get all the numbers here? You can double check it at home. So then if imagine you can also approximate the value of the average velocity in each interval is here, right? Where the average is the left and the right value, or specifically the V between 0 and 5, we can average of 25 plus 31 and divided by 2. That is the average velocity of this interval. It will give you another approximation, right? Okay, so the idea is that. Now, let us move on to the section 5.2, okay? I hope that we can do it faster today. In this section, we will talk about definite integral. Okay? You have the notes already. So this saves a lot of time for us. Remember, an approximation of this limit is the area under the curve, right? Sigma notation, or we expand it this way. Then we defined a definite integral. We write it as this sign from A to B of the function f of x dx. We defined it. There's the limit here. Limit from n go to infinity of the sum from n is equal to 1 to n of f of xi star delta x. Okay? The xi star are the same sample points. And the definite integral of the function f from a to b is written like this guy. Just a definition. Okay? The function f, we call the integrand. So if the function is integrable over the domain, then the function f, we call it the integrand. The value a and b are the upper and lower limit. Okay? So anyway, the final result of this integral will give us a number, right? X is a variable, dx is a notation. Okay, that's it. That is the definition. Are we good? Okay, just definition. It is suggested by Sir Leibniz. So there are some notes. First one, the integral from a to b of the function f of x dx, where x is the variable. It is a name, so we can rename it in the way we want. It is equal to integral from a to b of ft dt. It's just a name, so we can use another name for the variable. They're the same thing. It's still a number, right? Or we can use another letter. For example, integral from a to b of f r dr. Okay, just notation. The sum I from 1 to n of f xi star delta x, we call it Riemann sum. Riemann is a very famous mathematician. He died young, but yeah, you see him many times. In math. He's a great mathematician. His PhD advisor is Sir Gauss. Amazing. So, so as you can see, the integral, right, of the function f from a to b in geometry, you can imagine that it is a1. A1 is the area above the x-axis and below the graph. So in this case, these two give us a1, and this guy is a2, the area of this curve from a to b. Okay. So we can imagine this is the net area of a curve here. A theorem here, very important one. You can take a note in your notes. If f is continuous on the interval from a to b, and there's only finite jump, then f is integrable. If we can take the integral of f over this integral in intervals, we call it f is integrable. Okay, and it exists if there's finite jump. Okay, and yeah, this integral, we can write it in terms of limit of a sums, this, where delta x is the discretization, b minus a over n, and xi could be computed from this one, this formula. Okay.
So why can it have jump as continuities and still be like whatever can also be written in terms
Yeah, this theorem, to be honest, they prove it somehow, and I don't know if I can explain it here, but they proved already. With a finite jump, we can still
So
take
it
into
just has to be continuous, not differentiable.
yeah. If it has finite jump, then it is integrable. You see it. Okay? And here are some properties. The formula 5, 6, 7. You can write it down and prove it home. For the number 5, it's not hard to see. You can imagine this. The sum from 1 plus 2 plus 3 plus 4 plus 10. Oh, yeah. And the famous mathematician Professor Gauss did these problems when he was grade 5, if I remember correctly, when a teacher asked him to compute the sum from 1 to 100. Some student just you do it slowly, but he did a very smart way. For example, we add up to 100, right? He did it this way. I was told that, okay, we add this one, the first one, and the last one. Group it, 1 plus 100, 2 plus 99, 3 plus 98, etc. until the 40, 49 and 51. Wait. 2, 3 until 50 and 51, right? We see that each of them, the sum will be 101, right? And there are 50 pairs of these, okay? Yeah, and you go home and double check it, and it is this formula. So we have that, it is 101 multiplied 100 divided by 2, where n in this case is 100. It's amazing. And these are some properties of sigma notation. Sum of c, n times of c, it will be n times c. If each of the terms has c here, we can take it out of the sigma sign. Okay. Sum of from 1 to n of ai plus bi, it would be the sum of I from 1 to n of ai plus the sum of bi running from 1 to n. Similar story for difference. Okay. Now let us take a look at this example. Evaluate the Riemann sum of f of x. Riemann sum for the function f of x equal to x cubed minus 6x, taking the sample points to be the right endpoint. And a is equal to 0 b is equal to 3, and n is equal to 6. The second question is evaluate integral from 0 to 3 of x cubed minus 6x dx here. Okay, we're given the function and the intervals. Now, in the question A, we see that n is equal to 6. Therefore, what is delta x here?
One half.
Perfect. Thank you, Daniel. Is it Daniel?
Yeah.
Thank you. It is 3 minus 0, the endpoints, right? The difference of endpoints divided by the numbers of rectangles. It will be 1/2. Perfect. And remember, in the notes, xi will be a plus I multiplied delta x, right? You can go back to the notes and double check it. So it means that the points are xi, we can compute it. Okay. And the right hand points, we know that from the formula R6 is the sum from I is equal to 1 to 6 of fxi delta x, right? Right, the right endpoints. So, but in more details, let us write it down. Clearly here. Zero, 0.5, 1, 1.5, oops. 2, 2.5, 3. See that this guy is x0, right? This is x1, x2, x3, x4, x5, and x6 is 3. Okay, we know the xi's, right? And the function f is given already. So it will be what is it? F of 0.5, right? Multiply delta x, which is 1/2, plus f of 1 delta x, etc. until f of 3 multiply delta x, right? Are we good? And the function f is given as x cubed minus 6x here. So the first one, it will be 0.5 cubed minus 6 times 0.5, and then multiply with delta x, which is 1/2. Right? The second one, what is it, Harry? The second one? So the function f is given like this one. Right. This is the function f. And we want to evaluate the value of x1, and x1 is x2 is 1. Yes. Perfect. So that's it. And delta x, we computed here, 1/2, right? Then continue for other numbers, okay? And the last number will be, can you also help me with this? Evaluate the value of 3. Perfect, that's it. And the delta x is 1/2, right? Sum them up, it will be negative 3.9375. That is the right endpoints formula. Okay? You can double check it at home. So now let me give you an idea how to solve the question B. The question B that they ask us to evaluate the value of this integral. Okay? Evaluate from 0 to 3 of x cubed minus 6x dx. Okay? And from definition, and what do we know? We know that delta x is b minus a over n, right? And b is 3, a is 0, n is the number of the rectangles, which give us 3 over n, right? In general. And another formula, any xi, it will be a plus I times delta x, right? A in this case is 0. Delta x we just computed here. I is a number running from 1 to n. Okay? So we know xi. We're given the function f here. And the integral from 0 to 3 of x cubed, let us call it fx dx, right? From definition on the notes, you see that it is the limit from 1, n go to infinity of the sum from I is equal to 1 to n of f of xi delta x. Go home, play with this. You're given the xi's, right? Given the function f, and you can write down the limit explicitly here. And tomorrow we will continue. Okay? you, everybody.